In this video, we're going to go back and look in a bit more detail about what it means to be polar, and other than just looking at differences in ends, if there's something a bit more sophisticated we can do. So let's go back and let's look at a water molecule, which we said in a previous video was bent. So let's look at one of the HO bonds. We know that hydrogen has a lower electronegativity than oxygen. And in fact, hydrogen has a value of 2.1. You don't have to memorize this number. You would be given a table. You just have to know what to do with this number. Oxygen has a value of 3.5. So we look at the relative difference of these two numbers. So it's always the largest number minus the smallest number. And we can see that the difference is 1.4. Anytime the difference in electronegativity is greater than 0.5 but less than 2, we would say that that's a polar bond. Okay, so I clearly have polar bonds in water, so I'm eligible to have a polar molecule. You must have at least one polar bond to be eligible to be a polar molecule. We annotate polar bonds by drawing a line parallel to the polar bond. So here I've drawn it in red. I'm going to make it a bit thicker because I don't know how well the red is going to show. But I've drawn a parallel line to my polar bond. I know that oxygen has the largest electronegativity, so that becomes the head of my arrow. So the parallel line becomes an arrow. I know that hydrogen has the smaller of the two numbers, so it adopts that it becomes the tail of my arrow, but I annotate it with a plus sign. So I represent the tail of the arrow as a plus sign. The head of my arrow is just the head of the arrow. And for the plus sign, I write delta plus, and for the head of the arrow, I write delta negative. This is a lowercase Greek letter d, it means delta, and it just represents partial. So I've got a partial deficit of electrical charge here, hence the partial plus sign. I've got a partial surplus of electrical density over here, hence the partial negative sign. The partial reminds me and reminds the reader that this is not an anion or a cation. It's a partial increase or decrease, that's all. I could do the same here, so let's do this quickly. I would draw a line parallel to this bond with the head of the arrow at the oxygen, the tail of the arrow by the hydrogen, and I would represent the tail of the arrow delta plus, the head of the arrow delta negative. So now I've annotated both of my bonds in a water molecule. So I'm eligible to be polar because I've got polar bonds. But I'm only a polar molecule if I have a net dipole. So now I've represented the poles. Now I can just look at the poles to represent the molecule. So we're going to do some vector addition. So these lines, these red lines are vectors, and because they're trigonometric functions, you're allowed to relocate them. So I can move them. In a second, I'm going to put them tail to tail. What you're not allowed to do, you're not allowed to change the length, and you're not allowed to change the angle, because both of these things would affect the trigonometric function. So let's put these two red vectors tail to tail. So I've got this one here. I'll try and preserve the length. So this is that one here. And I'm going to put this one going up here. So I've done my best to preserve the angle and preserve the length. I've just relocated though. So I relocated this over here, and I kept this angle and length, and I just relocated it here, and I put them tail to tail. Now what we need to do is we need to draw a parallelogram. So to do so, I have to draw a line parallel to this vector up here, so it has to touch this head of the arrow here. Like that. So parallel line, hopefully you can see that. A parallel line to this vector, but touching this line. And then finally a parallel vector here to this vector, touching this line here. So this is a parallelogram. Notice I've got a point of intersection here. I'm going to draw a line from where the two original red vectors met to that new point here, and I'm going to draw this as a discrete vector. So I'm going to make that its own unique vector, and I'm going to call that C. I'm going to label the two original vectors A and B. Okay. So I know that C is equal to A plus B. So I've done vector addition. Now if C is greater than 0, I have a net dipole. So we don't really mind how large C is, so long as it's greater than 0. Clearly C is greater than 0. So this is why we say that water is polar. It's polar because it has a net dipole. Let's now have a look at carbon dioxide. Carbon dioxide looks like this. It's a linear molecule. It's a linear molecule. We look at values in a table. We know that oxygen has an electronegativity value of 3.5. Carbon is 2.5. And the difference is 1.0. 1.0 is greater than 0.5 but less than 2. So I know that these are polar bonds. If it's a polar bond, I would draw my line parallel to the double bond. The head of the arrow must be on oxygen because it's most electronegative. And the tail, which I make a plus sign out of, is on carbon. I do the same over here. Draw a parallel line, plus sign on carbon. The head of the arrow is on oxygen. And I annotate delta negative, delta plus, delta plus, delta negative. Now on this occasion, the two vectors are already tail to tail. So I would see clearly that I don't even have to redraw it. C must be 0. Because these two vectors are pointing in exactly opposite directions and have the same magnitude. So for example, if this vector were -1, this vector would be +1, and the sum would be 0. Whatever the number is, the sum would be 0. So C is 0, so there's no net dipole. So although carbon dioxide has polar bonds, it's eligible to be polar. Its shape won't allow it to be polar. So it's non-polar because it has no net dipole. So we have to distinguish, talking about bond polarity, and molecular polarity. Only molecular polarity is the true polarity that would be experienced. So what does polar mean? Polar means polar implies that it will experience extra intermolecular forces. So any molecule that's polar can experience dipole-dipole forces. The dipole is the net dipole. So two water molecules, they both have a net dipole. Those dipoles can interact. So if you imagine here the net dipole is C, you could have two C's interact. Let's have a look. You could have a C here and a C here. Well, let's annotate. We know the tail is plus, the head is negative. The tail is plus, the head is negative. So this would be a dipole-dipole interaction. You've got the delta negative of the head of one net dipole and the delta positive of the tail of one net dipole. So this gives a sticky quality to the structure. And we know that water tends to accumulate because of that attraction. Typically, polar substances manifest as solids or liquids. Non-polar substances typically manifest as gases. We experience carbon dioxide as a gas.